Hey, let's look at the back page of Chapter 7, Test Review, Worksheet number 2. Number 4, consider the graph f of x equals negative 1/2 x squared plus 8x. So that is the parabola that is drawn for you here. That is opening down. A line is drawn tangent to the curve at x equals 10. So you still want to plug this in your calculator because you want to figure out where x equals 10 is. And if you plug in your calculator and if you go to x equals 10 is going to be around where the graph begins to have a downward slope. And if and it says a line is drawn tangent to the curve at x equals 10, so if that's x equals 10, and if it has a downward slope, then I'm going to just right now just make an estimation and draw this tangent line. Okay, so first thing we need to do is we need to find the equation of that tangent line in point slope form and in slope intercept form. Okay. Now, if we want to find the equation of a tangent line, we need two pieces of information. We need the ordered pair, we need the point, and we need a point on the line, and then we also need the slope of that line so that we can put it into point slope and then convert it to be slope intercept. Now, we know a couple pieces of information. We know that the line is tangent to this curve. And if it's tangent, we know that means that they must share the same ordered pair. So if they share the same ordered pair, then that means I can plug 10 into this equation, and whatever y value I get, then that will also be the y value that is shared for this line. So if I plug 10 into this function, you can use your calculator to do that, you're going to get 30. Okay, so we have an ordered pair, 10, 30. Now, how do we find the slope? Well, if a line is drawn tangent to a curve, then not only do they share the same ordered pair at that point where they're tangent to each other, but they're also going to share the same steepness between the curve and the line. So if this curve, whatever the steepness, whatever the slope is at that point on the curve, that's also going to be the steepness for that tangent line. And so how do we get to our slope for that curve? Well, this is where derivative comes in. If we can find the derivative for this curve, and if we can evaluate the derivative at that point, then remember your derivative function is basically your slope finding formula, right? Whatever x value you plug into your derivative, in return, it will tell you exactly how steep it is on that at that point on that curve. So we can find the derivative. Negative 1/2 x squared becomes negative x once we bring down that 2, go through power rule. And then the 8x becomes 8. So this simplifies to be negative x plus 8. This is our derivative for our curve, and so therefore this is the slope finding formula for our curve. And then I can plug 10 into the derivative, and that'll get me negative 10 plus 8, which is negative 2. So our ordered pair is 10, 30. Our slope is negative 2. And so with these two pieces of information, we can plug into point slope, and that'll get us the first portion that we need for part A. Find the equation of tangent line in point slope form. So that's what we have. And then to get into slope intercept form, we just solve for y. So we add 30 to both sides, distribute the negative 2 through, and we'll get negative 2x plus 50. Okay, part B, find the area of the region bounded by the graph f of x, which is the curve, the tangent line, and the x-axis. So we're essentially looking for the area of this region. Now, if we want to find the area of this region, first thing we need to see is that we have to split this up into two definite integrals, because there's a shift in the bottom curve. So in this region, the top graph is the line, and the bottom graph is the curve. But then once we get past a certain point, then the top graph all of a sudden, well, the top graph is still the line, but then the bottom graph all of a sudden changes to the x-axis. So we also need to consider the bounds, because starting at this point, that is where our x value starts, so that's x equals 10. We also need to find this point, which is where the curve crosses the x-axis, and then we also need to find this point, and that's where the tangent line crosses the x-axis. So a couple of things that we can do to set up, to find bounds. You can either look for it on your calculator, or you can set the curve equal to the x-axis and factor out the negative 1x. You'll get x minus 16, so x equals 0 and 16. So the curve is going to cross the x-axis at 0 and at 16. And then to figure out where the line is going to cross the x-axis, we can set the tangent line equation, negative 2x plus 50, equal to 0. We want to find out where is this line going to cross the x-axis. Then we solve for x, we get x equals 25. So again, we need two definite integrals, one for this first region, and then a second one for the region where the bottom curve is going to switch. So then from 10 to 16, my top curve is going to be the line minus my curve. So top curve minus bottom curve between the correct bounds will give me the area for my first region. And then for my second region, from 16 to 25, so over here you see 16 to 25, top graph is the linear equation, and the bottom graph is the x-axis. And then the rest we can just plug in our calculator. The first region will give us an area of 36. The second region will give us an area of 81. So we get 117 square units. Okay, part B. It says the base of a solid is the region enclosed by the curve x equals 2 root y in the lines x plus y equals 0 and y equals 4. Now we need to figure out what these graphs look like. So something helpful to do is if we solve for y, then we can plug in our calculator. However, this is only the positive portion, so this is y equals x squared over 4. This is going to be a parabola, but it's only going to be a parabola in the first quadrant, because there's only a positive 2 root y. X plus y equals 0. That's the same thing as y equals negative x. And y equals negative x is simply going to be a linear graph with negative slope. And the line y equals 4. So here is my x equals 2 root y. Here's y equals 4. And here's x equals negative 2y. So we've identified the shaded region. Find the volume of the solid if all cross sections perpendicular to the y-axis. So the y-axis is vertical. Perpendicular would mean that 90 degrees, we're drawing a cross-section that is horizontal. And if it's horizontal, that means our base length will have to be in terms of y. Okay, we have to do cross-sections where they are right isosceles triangles, having the hypotenuse with one endpoint on the line and the other on the curve 2 root y. So let's label all of our graphs. We have y equals 4 here. We have x equals 2 root y. We have x equals negative y. This is already set up in terms of y, so we can do right curve minus left, or right endpoint minus left. So the right endpoint is at 2 root y. The left endpoint is at negative y. So 2 root y minus negative y is simply 2 root y plus y. So this is the base length of our hypotenuse. And then the formula for the hypotenuse as the base is 1/4 hypotenuse squared. So if this represents hypotenuse, we can plug this in the formula. So the area of the cross section is simply 1/4 2 root y plus y quantity squared. Okay. Now we're just not only finding area, we're also finding volume. We're actually finding the volume. So we have to plug it into the formula, which is the depth integral of the area cross section dx. So all this gets replaced with 1/4 2 root y plus y quantity squared. Our bounds are also in terms of y, so we can actually tell by looking at the graph. The lowest y value is 0, and the highest y value is just going to be a horizontal line, so we can find that is simply going to be 4. Now, if the line is curved, or if the line is curved, or if it is slanted, then we would have to set the equations equal to each other and find the highest y value, or look in our calculator. Okay, and then this can be plugged in our calculator. We'll get volume is 26.133. All right, 6 and 7 are integration by parts and tab method problems. So if you look at number 6, okay, if you look at number 6, we have the integral of natural log of 3x dx. Okay. We can't go through u substitution because we don't have an integral rule for natural log. So we look at integration by parts. We have the acronym where logs comes first, so LI, PET. We have logs versus algebraic, so we know logs is going to win out. So u is natural log of 3x, which means dv is going to be the remaining portion, which is 1 dx. So to get from u to du, it's u prime over u for natural log. So u prime is 3, our u is 3x. So 3 over 3x reduces to be 1 over x, and then we can also attach a dx there. To get from dv to v, we find the integral. So integral of 1 is simply going to be x. And now we can plug into our formula. U times v minus the integral of v times du. So this portion is done, but this portion, v times du, this cancels out to be 1. We still have to evaluate the integral of 1, which is x. Now we can combine our solutions together. So x, natural log of 3x, minus x, plus c. Okay, number 7. I want to bring the e to negative 3x up to the top to make it a little bit easier to deal with. So now we have 4x cubed times e to the 3x dx. If you look to try to go through u substitution, whether we let the u value be 3x, it won't cancel out the x cubed. And if we let the u value be x cubed, then we're not going to be able to cancel out that 3x, and we'll have too many x's left over. So we look to integration by parts. And we see that we have a polynomial versus an exponential, and polynomial is going to beat out the exponential. So then we can let the u value be 4x cubed. We can let the dv be the e to the 3x. Now, because we have a polynomial of degree higher than 1, this could mean that we have to go through integration by parts multiple times. So to make things more efficient, we can go through tab method. So we'll let the u value be 4x cubed. We'll let the dv be e to the 3x. Now again, this tab method will only can only be used if you can assign the u value to be the polynomial. Okay. So and we go through the acronym LIPET to make sure that we've assigned the correct u value for with the polynomial. Okay, so on the first column, we can simply find the derivative of each term until we get to 0. And then on the right, we're going to keep finding the indefinite integral until we've done it the same number of times as the left side. So I'm going to go through the integral of e to the 3x once, and then we'll see the pattern that we can use over and over again. So the integral of e to the 3x means we have to go through u substitution because we have 3x, that's more than just an x. There's going to be a coefficient that's going to be produced. So let u be 3x. Our derivative is 3. dx is du over 3. We make our substitutions. So we get e to the u times du over 3. The 3 can be pulled to the front. So we have 1/3 integral of e to the u. And then we're left with 1/3 e to the 3x plus c. So basically, every time we find the integral of e to the 3x, we're always going to be producing 1/3, okay, because that's du over 3. So knowing that, the integral of e to the 3x will give us 1/3 e to the 3x. If we find the integral again, it'll produce another 1/3. That'll give us 1/9. Okay. Find the integral again, it'll produce another 1/3. So 3 times 9 is 27. Find the integral again. Again, we'll produce another 1/3. So 27 times 3 is 81. And then we can assign alternating signs, starting with a plus, minus, plus, minus, plus. And then we're going to combine diagonal terms. And these will show which terms will be multiplied together. Now, when all these are multiplied together, there's going to be e to the 3x that's going to show up with each term. So I went ahead and I just factored out the e to the 3x so I didn't have to write it so many times. And then just combine the rest of the terms. 4x cubed over 3, 12x squared over 9, a minus, plus 24x over 27 minus 24 over 81, and then finally plus c.